Before we get started, any questions from last time? Okay, I'm going to just begin by taking a moment or two to review from last time. Well, first I'll review from a week or so ago. So, in the time-like case, we considered a space-like surface, hypersurface, of codimension 1. Then we looked at the orthogonal geodesics, which of course, the geodesics are orthogonal to a space-like surface or time-like. And with very little effort, we got a canonical form for the metric near a space-like hypersurface. That took this form. You could describe it by saying we imposed some gauge conditions. But it was useful to understand that the gauge conditions, well, first of all, they can be imposed, but the geometrical meaning of imposing them is that we were looking at the orthogonal time-like geodesics to the surface. And that perspective helped us understand what it would mean if this coordinate system became bad. And then, magically, Einstein's, in general, rather complicated equations gave a very simple interpretation to one component of the Einstein equations, the TT component. Now, we wanted to do the same thing with, so, that reminds me that the second homework is on my website. And also it will be on Canvas, where you can submit the homework. So we wanted to do something similar with light-like geodesics, but in that case we couldn't consider a codimension 1 space-like surface simply because a light-like geodesic can't be orthogonal to a codimension 1 surface. No matter which way a light-like geodesic goes, here or there or whatever, it can't be orthogonal to a space-like surface of codimension 1. So instead we considered a codimension 2 surface. A codimension 2 space-like surface, which we can think of as being embedded inside a codimension 1 surface. From a codimension 2 surface, W, it's hard to draw the picture on a two-dimensional flat blackboard, but you can have outgoing null geodesics that are orthogonal to a codimension 2 surface. So for example, if our surface is a sphere in ordinary three-dimensional space, the light rays that go outward from the sphere at the speed of light are the orthogonal null geodesics in that case. A second family would be the ones that go inward at the speed of light. So there are two families of future-going orthogonal null geodesics, the ones that go out and the ones that go in. And magically, there's a theory for this that's very similar to what happens in the space-like case. So we put the metric in a canonical form. Well, okay. In this situation, there's a d-1 manifold we're interested in. The union of these geodesics. So we have our codimension 2 surface, space-like surface. Going out from it is a d-2 parameter family of null geodesics. Together they will sweep out at least near the initial surface a d-1 manifold, which I'll call Y. So we had a canonical form of the metric near W and in fact near Y. The canonical form was, I won't repeat the derivation. I'm just going to write the answer we got last time. Where W is U equals V equals 0, and Y is just V equals 0. And Y is swept out by the curves xa equals constant, and of course V equals 0, since that is the condition to be in Y. So these curves are parameterized by U. And in fact, U is an affine parameter for these geodesics. So in this formula, so Q is independent of U at V equals 0, but there's no other constraints. On the functions Q, G, A, B, and C. Otherwise, except for the one fact that Q doesn't depend on U at V equals 0, all the coefficients that appear in this formula are completely general functions. So we could have, again, described this metric by conditions analogous to these. I'll let you think about what they would have been. But you could have formulated this in terms of constraints on D components of the metric tensor. But such a formulation wouldn't have given much insight about what the formula meant. What this means, well, what we've explained is that this is the coordinate system that's adapted to the outgoing null geodesics from W, and more generally the outgoing null geodesics from W epsilon, defined by V equals epsilon. So these are all, the initial value surface S contains W, but it's swept out by these W epsilons, and each W epsilon is the source of what we could call Y epsilon. Y epsilon, so W epsilon is V equals epsilon, U equals 0. Y epsilon would just be V equals epsilon with no condition on U. So each Y epsilon is itself a D minus 1 manifold swept out by a bunch of null geodesics. Now, as in the derivation was longer, and the reason in this case the derivation was almost immediate. In this case, the derivation was a little bit longer and messier, and the reason was we started with W, and to get this picture we had to introduce V, which we didn't start with, and then the W epsilons, and then finally we put it in this form. So the derivation is longer because we started in codimension 2 instead of codimension 1, so there were more steps. But the final answer, in many ways, is very similar. And the most important relationship is that the rate, well, one component of the Einstein equations in this coordinate system comes out to be amazingly similar to the TT component of the Einstein equations in this case. Before I go back to that, though, I want to say one more thing, which is we should ask, when can this coordinate system break down? Well, there actually are only two possibilities, which is the space-time itself may end, by this I mean the following. To construct this form of the metric, we started on W, and then we looked at the outgoing null geodesics parameterized by an affine parameter U, and we followed them into the future. They may or may not extend up to u equals infinity. The space-time might end. Informally, we might reach a singularity, a value of u past which we can't continue. In fact, the goal today will be to explain Penrose's theorem, which gives a sufficient condition under which that happens. So we definitely have to be aware that the space-time may break or end, in which case there will be an upper bound on u for some or all of these null geodesics. An upper bound on u for some or all values of the other coordinates. So if a single null geodesic can't be solved, isn't complete, can't be made complete by solving the geodesic equation to all values of u, that's a signal of some kind of incompleteness or singularity of the space-time. The space-time might end, and in fact, we're aiming to prove that under certain conditions it will. So we need to be aware of that possibility. Now, as long as the space-time itself doesn't end, there's only one other thing that can go wrong, and it's the same thing that could go wrong in the previous case. In the previous case, we tried to parameterize a point in space-time by how long in proper time it was from S and where the geodesic that reaches it originated on S. In other words, we swept out space-time by a point on S together with the geodesic, and if we were lucky, given the geodesic and also given the initial position of the geodesic and also the time along to the geodesic, that was supposed to be a set of coordinates for a space-time point. But we know that that fails if these geodesics intersect, or even if they have a focal point, meaning that infinitesimally they try to intersect. Now, we're in the same situation here. To find this coordinate system, we start at a point on one of the w epsilons, which just means a point in S, and then we take the null geodesic, outgoing null geodesic, orthogonal to w epsilon, and we solve the geodesic equation. And generalities about ordinary differential equations will tell us that the solution is real analytic as long as the coefficients of the equation are real analytic and the initial conditions are real analytic. If we don't reach the end of the space-time, that means that the equations are real analytic and the initial conditions were real analytic. So the solution is real analytic as long as the space-time doesn't end, meaning the functions q, g, and c are all going to be real analytic functions. Now, given that, what can go wrong? The metric is a well-defined d by d symmetric matrix, but it could fail to be non-degenerate. The only thing that could go wrong is that this metric tensor could become degenerate. But e to the q isn't going to vanish, which would mean q going to minus infinity, because v was independent of u. Q was independent of u at v equals 0. So this little bit remains non-degenerate. And we could have done that at any value of v, incidentally. We just are focusing on v equals 0. So the only thing that actually can go wrong is that the matrix, the d minus 2 by d minus 2 matrix GAB could become degenerate. So the second thing that can go wrong is that we might have determinant of GAB equals 0. But that's actually the condition for a focal point. Because GAB measures the distance in the manifold Y between two neighboring orthogonal null geodesics. And if GAB is going to 0, it means that two of the null geodesics that are initially slightly displaced from each other and orthogonal to W are actually converging. So as in the time-like case, the only things that can go wrong are either that the space-time itself ends, which we will prove under certain conditions. In the time-like case, we proved that with Hawking's theorem. Or the determinant of GAB could become 0, which is the condition for a focal point. So the strategy is we're reversing history because Penrose was first before Hawking. But the strategy will be the same as in the way we've presented Hawking's theorem. We're going to find a condition under which we can predict that the determinant of GAB has to go to 0. And then knowing that, we'll actually be able to find a condition under which the space-time has to end. Any questions? Now, I wrote down last time, then we define what's called the expansion. One over A dA du is called the expansion. It's also the same as, I think it's the same as half d by du of the square root of the determinant of g. And then we also had last time sigma, which is a half of g inverse dug minus the trace. And then I remarked last time that there's a formula for the UU component of the Ricci tensor. I hope I have that right. Which looks exactly the same as the analogous formula for RTT in the time-like case, except that in the time-like case we had d minus 1, and here there's d minus 2. That comes from the fact that now GAB is a d minus 2 by d minus 2 matrix. In the other case, it was d minus 1 by d minus 1. It seems magical that this formula for RUU is so similar to the formula for RTT in the other case. Anyway, checking this formula is problem 1 on the problem set, so I won't do the computation for you on the blackboard. Now, because the structure is the same as in the other case, we can essentially do the same computation we did in the other case to prove the existence of focal points under certain conditions. So we say exactly the same thing as before. If at u equals 0, theta is equal to w, or minus w, let's say, where w is positive. So if theta is negative at u equals 0, then well, okay. Well, we use the null energy condition. Which says that TUU is non-negative at each space-time point. And that tells us that the right-hand side is less than 0. As I remarked last time, the null energy condition is far more robust than the strong energy condition used in Hawking's theorem. The null energy condition is satisfied in all reasonable classical field theories. Certainly all standard ones. I think all reasonable ones. But definitely all the classical field theories that are most often discussed. So it's reasonable to assume the right-hand side is negative. That tells us that if I divide by theta squared, the right-hand side is still negative. So I can write that in the form d by du of 1 over theta plus 1 over d minus 2, minus d by du of 1 over theta plus 1 over d by 2 is negative. And after the same manipulation as last time, well, what do we learn from this? So we learned that 1 over theta is bigger than u over d minus 2 minus 1 over theta at u equals 0. We get an upper bound on theta that tells us that it goes to minus infinity. Gosh, I don't have it. By the same elementary calculation we did in the time-like case, but with d minus 1 replaced by d minus 2, we get an upper bound on theta, except that I don't remember if I called it theta in the time-like case. And that shows us that theta goes to minus infinity at u equal to or less than d minus 2 over w. So we get an explicit upper bound on when u goes to minus infinity. But since u equals dua over a, the only way for u to, and a is going to be a smooth function. A can't go to plus infinity. It might go to 0. Right? Part of the real analyticity is that the only thing that a can do, which is bad, is go to 0, as long as the space-time is good. So theta going to minus infinity means that a goes to 0, or maybe the space-time ends. So, assuming the space-time itself is good, theta going to minus infinity happens because, sorry, not u is dua, theta was defined as dua over a. And the way for theta to go to minus infinity is that a goes to 0. For example, dua can't go to minus infinity. That's part of the real analyticity. Yes? No, I don't think so. I think this is correct, but
It should be over
what?
the determinant.
Ah, okay. Sorry. Is that correct? Yeah. Okay. You're right. Because yeah. Sorry. That's right. A is the sorry. If you want a half, then I shouldn't have the square root. Right. A is the square root of the determinant of g. So, just rewriting this, it's 1 over the square root of the determinant of g times d by du of the square root of the determinant. But you can also get rid of the square root, which I tried to do, but I left out the factor of det g. As Herman says, we could also write it as a half d by du of the logarithm of the determinant. Any other comments or questions? So, well, what makes this remarkable is that it only involves conditions at one point. All we need to know is infinitesimal data just near this point. And that lets us predict that what will happen to this geodesic, it'll either end or else focus with its neighbors within a bounded affine parameter. So Einstein's equations are very complicated nonlinear equations. It's usually very hard to learn anything except by solving them everywhere. But in this amazing case, you can learn something useful by just studying Einstein's equations along one geodesic and its immediate neighborhood. That was also true in the time-like case. And as far as I know, this situation with the Rayleigh-Story's equation is the only situation where you extract something useful dynamical information from Einstein's equations by such local considerations. Now, what is it going to be good for? Well, the first thing we'll show it's good for is proving Penrose's theorem. But what's Penrose's theorem about? So let's remember a Schwarzschild black hole, first of all. Well, I've written it in 4 dimensions. There's a simple generalization in any dimension. So that's the Schwarzschild solution. And for r bigger than 2gm, t equals time, a causal path can only go forwards or backwards in time. You can't stand still in time. You can't make time stand still. But for r less than 2gm, 1 minus 2gm over r is negative, and the roles of t and r are exchanged. So you can stand still in t if you wish, when r is less than 2gm, but you can't stand still in r. Time's inexorable passage forces you to greater or lower r, depending on which is the direction of the future. So I hope, I'm not intending to describe Penrose diagrams. I'm hoping, well, I will give a very brief explanation, but not self-contained, of what's a Penrose diagram. And I'm hoping most of you are familiar with them already. Otherwise, you might, for example, look at Wald's book to brush up on Penrose diagrams. I will draw the Penrose diagram of a collapsing star, and I'll very briefly explain what the diagram is showing. So in this picture, spherical symmetry is assumed. So time runs upwards, and space runs horizontally, but we only depict the radial direction. Spherical symmetry is assumed, so there are polar angles that aren't drawn. If we're in 4 dimensions, the polar angles theta and phi aren't drawn. And what's drawn roughly corresponds to time and radius. But remember, we can't assume that r represents the radius because we've discovered that when r is less than 2gm, it becomes a time coordinate. And it's t that behaves more like a radial coordinate. So with that said, let me finish drawing the diagram. So time runs vertically, space runs horizontally, but a conformal mapping has been made to map the picture into a finite one that I can draw on a blackboard. It would be hard to draw time and space going to infinity on a finite blackboard without compressing them. And Penrose has made a conformal mapping to put the diagram in a situation where light rays, future-going light rays, are at a pi over 4 angle to the vertical. I've tried to draw that. On this picture, I haven't drawn it very accurately, but these 3 lines are all meant to be at pi over 4 angles to the vertical. The left boundary is just the center of symmetry, the center of spherical symmetry. Normally that would be r equals 0, but we have to be more careful here. Then there's the part of the picture that's filled by the collapsing star. So the far past is at the bottom. Far past means time goes to minus infinity. Spatial infinity is this corner. That's r goes to infinity. Let's say with r much greater than t. Then what's called null infinity. Well, past and future null infinity are here. What's meant by null infinity? Well, null infinity means that r goes to infinity, but t minus r is fixed. So if you're looking at an outgoing massless radiation, it will propagate to t equals infinity, but the retarded time, t minus r, which in flat space would have been the time when the signal was emitted, assuming it came from the origin, is fixed. So outgoing massless radiation ends here, and past infinity, null infinity in the past, t goes to infinity with t plus r fixed. And finally, future infinity is here. That's t goes to infinity with fixed r. So if you and your spaceship and you're a time-like observer or keep staying at fixed r, watching this space-time, you'll somehow move around in here and end up at this point. That's where time goes to infinity at fixed r. Or, in general, time goes to infinity with r much less than t. Instead of saying fixed r, I could just say that r is much less than t. You'll still end up here. So the various ways of going to infinity with different relations between t and r correspond to the past, spatial infinity, future infinity, or null infinity. Then this wiggly line up here is the Schwarzschild singularity, where r is 0. Now, part of the space-time is filled by the collapsing star. That's this thing here. So the collapsing star, well, I'm assuming it was made from massive particles. If so, it came from the far past with r much less than t. So I drew it as emanating from this point. If the collapse partly came from ingoing massless radiation, I'd have drawn the star more like this, because it could have occupied part of past infinity in the past. But if it was made from tables, chairs, and other massive objects, then it originated down here. Now, this very important diagonal line is the horizon. So that diagonal line is at a pi/4 angle to the vertical, meaning it depicts an outgoing radial geodesic. Clearly, if you're to the right of that line, on a causal curve, you can escape to infinity at the speed of light. If you go outward with the pi/4 angle from the vertical, you'll stay away from this one, and you'll reach null infinity. You don't have to go at the speed of light. A time-like path would have reached future infinity, or could have reached a later point in null infinity. Not the soonest one that a massless light ray would get to, but still somewhere. You'd have to accelerate to asymptotically close to the speed of light, but if you are able to do that, you'd get up there. In the real world, you probably don't have rocket engines that would do that, but classical general relativity would allow it. If, however, you're behind the horizon, then try as you might, all you can do is go toward the future, and wherever you go to the future, you'll end up on the singularity. So this space-time ends on a singularity. Well, actually, what is the solution for this space-time? Well, outside the surface of the star, it's just a piece of the Schwarzschild solution. Inside the surface of the star, it's harder to give an explicit solution, but for example, there's the Oppenheimer-Snyder solution in the case that the star just consisted of collapsing dust. In that case, you can find an explicit solution for the non-Schwarzschild part, the interior part. In a more realistic model, that would be complicated. So when Penrose arrived on the scene, this much was more or less known, although not as nicely explained as one can do with Penrose's diagrams. And although I said I wasn't going to explain them, I did a little bit more than I was intending to, because I had no idea what fraction of you actually know about Penrose diagrams. So I didn't want people to be completely lost. Anyway, this much was known with perfect spherical symmetry, but Penrose asked the question, suppose you don't have perfect spherical symmetry. To what extent can you show that there is a similar picture to this one? Oppenheimer and Snyder had showed that if you have perfect dust, well, it'll collapse to a point, but you could worry that in Newtonian physics even, perfect dust could collapse to a point. What would hold it up? And what would happen if you have a more realistic equation of state and if it isn't perfectly spherically symmetric? Anyway, Penrose wanted to show that there was a qualitatively similar behavior, even if you didn't have the idealized situation that you can solve explicitly. So he proved what I will call Penrose's theorem. Well, we're going to navigate toward Penrose's theorem. He proved a theorem that shows that a space-time that satisfies certain conditions that are satisfied by anything sufficiently close to Schwarzschild is going to be incomplete toward the future. Now, his key insight was the notion of a trap surface. Sorry. So let me to explain the notion of a trap surface, I want to say a little more about the Penrose diagram, actually. But I'm going to erase some of the stuff we cluttered the picture up with so we can see it better. Now, remember that each point in the diagram represents a sphere in M of some radius r. Now, that's a well-defined statement because spherical symmetry is assumed. So each point represents a sphere, and the metric on the sphere is assumed to be spherically symmetric. And a spherically symmetric metric is just r squared d omega squared for some r. So there's a well-defined function r on this spacetime. Or more generally, on any spherically symmetric spacetime, there's a well-defined function r. At each point in a spherically symmetric spacetime, you have a sphere of some radius r. So that's a well-defined function. It'll be, well, in the part of the spacetime outside the collapsing star, it'll be the function that appears in that version of the metric. Inside the star, we don't know in general what it is. But first of all, there is a well-defined function r on this whole picture. Now let me tell you the values it takes. So r is 0 at the center of spherical symmetry, but r is also 0 at the singularity. R is equal to 2gm on the horizon. So I'm assuming you all know enough about Schwarzschild to know that if you analyze light outgoing geodesics, well, okay. I'm going to assume that statement is known. R is infinity in various other places in this picture. And at this point, we actually have all possible values of r. Also at this past infinity. So past and future infinity, the time is infinity or minus infinity. And r, say in the past, is 0 on this line, infinity on this line. So it's not a continuous function near that corner. Now, suppose we're behind the horizon. Behind the horizon is a two-sphere. I mean, each point behind the horizon represents a two-sphere because each point anywhere in the picture represents a two-sphere. Now, go on any causal path starting at that point. Well, the function r decreases along any causal path. So a first approximation to Penrose's insight is just to observe that this function r that we defined is decreasing along any causal path. A slight improvement is to say that the area, 4 pi r squared, decreases on such a path. The reason that's an improved statement is that Penrose wanted to formulate things in a way that didn't assume spherical symmetry. The definition of the function r required spherical symmetry, but it doesn't take spherical symmetry to imagine some two-sphere behind the horizon. You wouldn't have a preferred one, and the metric won't be spherically symmetric, it'll be lumpy, but it'll have some area. So instead of saying that r was decreasing along a causal path, he said that the area of the corresponding surface was decreasing along the causal path. So one hypothesis about generalizing the known case is to take a surface with the property that if you move it forward along any causal path, its area would go down. But that turned out to be too strong. What Penrose discovered is that instead you should look at the outgoing and incoming null rays from the surface. And that leads us to the idea of a trap surface. trap surface has W is a codimension 2 space-like surface. And it has an area. A surface is trapped if its area decreases. So we pick outgoing null geodesics. We look at the two families of outgoing null geodesics. We parameterize one by U and the other by V. And we have the two expansions, dUA over A, dV A over A. A surface is trapped if its area increases if it tries to go either out or in at the speed of light. Well, sorry. I didn't say that precisely enough. I should have said that A is the area density. So A is the square root of the determinant of GAB in the previous discussion. So this is a pointwise condition on the surface. At each point on the surface, locally, if you move outward in either null direction, the area goes down. I'm afraid we need a different symbol for the integrated area, maybe curly A. Curly A is the integral of the area density over W. So it's the area density that I'm calling A. And the condition is that the area density is originally decreasing along each light-like curve. Now, the motivating case for this definition is a sphere in the Schwarzschild solution. The light-like curves are null curves on which R can only go forward toward R equals 0. So the area is decreasing in either light-like direction. Yes?
What happens if you consider the area along any causal curve? You said it's too strong. Why is that?
Well, by considering only the extreme ones, Penrose got his theorem. We'll get to it in a little bit. I'm not going to tell you you can't prove something useful by considering other causal curves, but it didn't lead to Penrose's theorem. You have to think of something new. But part of the answer is that although in Schwarzschild, well, okay, I think I'd like to stop there. So considering the extreme ones, we'll find something very interesting and useful. Maybe there's something else one can say. Let's just look at some surfaces. So for example, here's a two-sphere. This is meant to be a two-sphere in Minkowski space. And let's say that U parameterizes the outgoing geodesics, V parameterizes the in ones. This is an example where theta out is positive and theta in is negative. Right? If you take a two-sphere in a Minkowski space and you move outwards at the speed of light, you're increasing the area. Move inwards at the speed of light, you're reducing the area. This is a local statement. We could move outwards uniformly everywhere, and that will increase the area. But just moving outwards a little bit in one little region will increase the area. Because the function theta u is positive pointwise. I mean, that's a pointwise statement. So wherever we move the surface outward at the speed of light, its area density is increasing. If you move it inwards at the speed of light, its area density would be decreasing. Now, it's not hard to give an example in Minkowski space of a surface with the property that both theta u and theta v are not everywhere positive. All we need to do is to consider a kind of lumpy sphere. might be a little hard to draw, but you see, where it bends out, the outward rays would cause the area to increase. But where it bends in, if you go outward, you're actually decreasing the area. So in this picture, theta u is positive, but theta v is negative at the bottom. But over here, it's opposite. And Penrose, you could ask yourself, in Minkowski space, can you embed a sphere or any other Riemann surface of higher genus in such a way that theta u and theta v are both everywhere negative? You'll probably sort of convince yourself intuitively that you can't do that. And that's a special case of what follows from Penrose's theorem. Any questions on the notion of a trapped surface? So remember, the prototype of a trapped surface is the surface defined by a point behind the horizon, in this situation, the spherical symmetry. So what Penrose did was to abstract the fact that the area of that surface would go down along outgoing light rays as well as ingoing ones to a general definition of a trapped surface. And then he proved that any space-time with a trapped surface will be incomplete. Yes?
I have a question. Could you comment on what happens at the center of spherical symmetry inside the horizon? This little line segment there.
Nothing happens here until you get up there. Well, the sort of fact that I'm not explaining systematically, because I'm assuming most of you have had a prior exposure to general relativity, is that you notice nothing locally when you cross the horizon. That's true for an observer here, but it's also true for an observer inside the star. So, in fact, which line is the horizon can depend on what happened later. If I would, long after the star collapses a million years later, I throw in another table or chair, the horizon would be farther out than it would have been. So causality tells us that you detect nothing along this line. But this part of the diagram was a little bit speculative when Penrose was working. For the exact Oppenheimer-Snyder solution, one knows that this part of the picture exists. But in general, one doesn't have an exact solution for a more realistic matter system. So you could put a question mark on this part of the picture. But outside the surface of the star, we have the Schwarzschild solution, and we know exactly what's happening. If you like, part of Penrose's motivation was to get some insight about what has to, to get some insight showing that the picture has to be similar for more realistic matter systems, also without spherical symmetry. Any other questions? Yes?
Is there a notion of trapped surface that's not codimension 2, like codimension 2? Like, I'm wondering if I can have a singularity in some dimensions, but not others.
Well, the question of in what is codimension is a singularity, as we'll discuss later, perhaps little is known. So the answer to that is yes, and we don't know much about it. But I've told you about two cases, space-like codimension 1 and light-like codimension 2, where Einstein's equations do magical things. If you want to do something else, you're kind of on your own. They're highly nonlinear equations and very difficult to understand. Any other questions? Yes?
So inside the horizon, is there a well-defined notion of which direction of causal path tends towards the future in the sense of an arrow of time and increasing entropy from?
Well, forget about entropy. In this picture, future going means within a pi/4 direction of the vertical. That was implicit in my statement that future going causal paths go to smaller r.
But does that relate to what an observer who's inside the horizon would experience as time goes forward?
Yes, that's what general relativity says. Yes?
About the defining W as a space-like surface inside of the horizon, I guess it's clear in Minkowski space that we just take like r equals constant or something. But when
We assumed spherical symmetry. If I assume spherical symmetry, then space-time is a two-parameter family of spheres.
I guess I'm wondering, when we say it's space-like, but we're on the left side of this horizon, does it, given that the sign switches in the back?
I'm going to repeat what I said. We have a space-time which we assume is spherical symmetry, and we assume that the orbits of the symmetry group are spheres. Now, any such space-time is a two-parameter family of spheres. And its most general metric would be of the form GAB, dxa, dxb, where a and b are 0 or 1, plus some function r of xa squared, d omega squared. That's the most general form of a metric with spherical symmetry and the orbits being spheres. So there are two things in the game. One is a two-dimensional geometry, and the other is a function, r, on that geometry. So since space-time by definition is a smooth manifold, the two-dimensional geometry is a smooth manifold. That two geometry is what's been drawn on the blackboard. However, in drawing it, I made use of Penrose's trick of a conformal mapping to conformally map it to finite distances so we can see it and talk about it better. But apart from the conformal mapping, this picture is simply this two geometry. And then we have a function r on that two geometry. Any other questions? Yes?
About the coordinates there, like u and v, when you define the coordinates, it was adapted to the outgoing algebra.
We should do it again, a mirror image version adapted to the incoming ones. So I oversimplified it slightly. U is an affine parameter on the outgoing geodesics. V is an affine parameter on the incoming geodesics. So in the way we derive the Raychaudhuri's equation, well, I didn't say anything about exactly how to define V. We could have made it be an affine parameter on the ingoing geodesics. Well, I might say the positivity condition doesn't depend on U being an outgoing affine parameter. It just depends on U being a parameter that increases along the geodesics. So actually, the V we defined, even though it wasn't an affine parameter, was good enough for the statements to make sense. But you're correct that in developing the theory, there was an asymmetry between U and V to study the outgoing guys. We should reverse it to study the ingoing guys. So I wouldn't use the same coordinate system for either one. Any other questions? Okay, now we get to Penrose's theorem. I jumped the gun by writing it on the name on the blackboard before, forgetting I hadn't introduced trap surfaces yet. So here are the assumptions in Penrose's theorem. M is globally hyperbolic. With a non-compact, and this is crucial, as you'll see, initial value surface S. So, for example, we could be studying gravitational collapse in asymptotically flat spacetime, or in an open FRW universe. Either one has non-compact initial value surfaces. 2 is we assume the strong energy condition. Not the strong energy condition, sorry. The null energy condition. And the third property is that M has a trap surface. Under those conditions, we learn that M is not geodesically complete. Sorry. M has a compact trap surface. we won't get anywhere with just a little tiny piece of a trap surface. We need a compact trap surface. So M is not geodesically complete, and more specifically, at least one orthogonal null geodesic from M ends. When I say it ends, I mean it can't be defined up to infinite affine parameter. It ends at a finite value of its affine parameter. So a motivation is that in the Schwarzschild case, we have this point that corresponds to a trap surface. The outgoing and incoming null geodesics actually all end in a finite value of the affine parameter. It's obvious in the picture that they all end at a finite value of the Schwarzschild time. It's slightly less obvious that they end at a finite value of the affine parameter. Maybe I should have put that on homework. But anyway, it's a true fact. So Penrose wanted to prove something like this in general, but he proved something much weaker that happens in Schwarzschild. In Schwarzschild, the in and outgoing null geodesics all end at a finite value of the affine parameter. In general, Penrose only proved that some orthogonal null geodesic ends at a finite value of its affine parameter, so that the spacetime is geodesically incomplete. What's that? Oh, W, thank you. Any other comments or questions? Okay, so the idea is to look at the boundary of the future of W. The reason we spend so much time talking about the boundary of the future is that Penrose's theorem involves looking at the boundary of the future of a trap surface W, and other applications we'll discuss in the next week involve the boundary of the future of various sets. So we know that the boundary of the future, so we know that if P is in the boundary of the future of W, then there exists a prompt null geodesic from W to P. So if we take, so the boundary of the future of W is contained in the union of all orthogonal null geodesics from W. If we simply brutally take the union of all orthogonal null geodesics, we'd get a set that contains the boundary of the future of W. But that would be too much, because we know that a point on an orthogonal null geodesic isn't in the boundary of the future if it's after a focal point. So we could do better if we say that, actually, the boundary of the future is equal to the union of the prompt parts of all orthogonal null geodesics from W. Because each point in the boundary of the future can be reached by a prompt curve, which is one of these orthogonal null geodesics. So to investigate this, let's look at a particular gamma. A particular orthogonal null geodesic, and ask, is the prompt part of gamma compact? Well, the answer is yes if a gamma has a focal point. I think I explained this in the last lecture, but because it's an important point, I'll just remind you. if gamma has a focal point P, then anything after P, the part of gamma after P isn't prompt. The part of gamma up to and including P is a closed set. It might not be, well, it might not be entirely prompt, but okay. We use the fact that the boundary of the future of W is closed in M. So by set theory, this is actually what I should have said first. Its intersection with gamma is closed in gamma. So, as I think I actually said last time, the only options are it could equal, one option is to equal gamma, and that would be not compact. Or it could equal an initial part of gamma, an initial closed interval in gamma, and then it is compact. So if gamma remains entirely in the boundary of the future, then the part of gamma which is in the boundary of the future is all of gamma, and that's never compact. But if gamma eventually leaves the boundary of the future, then the prompt part of gamma, the part in the boundary of the future, is an initial closed interval, and it is compact. So if gamma has a focal point, we're in this case. So that explains that if gamma has a focal point, the prompt part of gamma is compact. Now, in the hypothesis of Penrose's theorem, we're given that theta u equals they're negative along W. In other words, at u equals v equals 0. Since W is compact, so they're uniformly negative. There is some lower bound, positive, negative upper bound. There's some W greater than 0, such that theta u and theta v are everywhere no bigger than minus W. If they're negative on a compact manifold, then there's some lower bound strictly less than 0. So we learn, therefore, from Ricciardori's theorem we learned that each gamma has a focal point at u equal to or less than d minus 2 over w, or v equal to or less than d minus 2 over w. In other words, the outgoing and incoming ones have an upper bound on the value of u or v of the first focal point, which is d minus 2 over w. So we proved that unless the space-time ends, each gamma has a focal point. So if M is geodesically complete, each gamma has a focal point. So each boundary of the future intersect gamma is compact. But, you see, a point in the boundary of the future is determined by what data? Well, there's an initial point on W, let's call it Q. Then you decide to go out or in. And then you travel out or in for an affine parameter distance that's bounded by d minus 2 over W. So the data describing a point x in the boundary of j positive W is determined by the following data. There's a point in W, a choice of out or in, and then you pick U or V, which is in the set from 0 up to focal point, which is a compact set. So the choice of Q is in a compact set. The choice of out or in has only 2 values. And then U and V range over a compact set. So we conclude that if each gamma has a focal point, we would conclude that the boundary of the future is compact. It was made out of closed intervals of bounded length parameterized by a compact set. Any questions about that? Well, how do we finish the proof? Well, we know from previous lectures that the boundary of the future of W is an achronal manifold of codimension 1 and isomorphic to part of S. So as I actually said last time, a manifold that's part of S and has the same dimension as S is either S itself or an open set in S. That's why it's important here that S isn't compact. Since the boundary of the future, if S isn't compact, then neither S nor any open set in S is compact. So this is a contradiction. It's impossible for a compact achronal manifold to be either S or part of S. So that concludes the proof of Penrose's theorem. That's why in the last couple of weeks I've several times explained the fact that any achronal set can be embedded in S. And then we emphasized that the boundary of the future of a set is a manifold. And, the boundary of the future is an achronal manifold. So it can be embedded in S. And if it's compact, S would have to be compact, and this manifold would have to be all of S. So this is how Penrose proved that the existence of a trapped surface, together with the null energy condition, and a non-compact initial value surface, implies that space-time can't be null geodesically complete. Any questions on that? Yes?
I guess one obvious question is there anything you want to still say in closed?
Well, I'm going to discuss an example of a closed universe in a moment. So we'll have some fun things to say, but you can ask your question again after I describe the example. Any other questions? Yes,
take the inward going black
Yes.
they converge at the
yes,
center. And that's and then if we wiggle it a little bit, we get the caustic
yes,
going in, and that's just the DUAO statement of.
Richard Orr's there, right,
But we also have the outgoing ones that don't do that.
right.
So what's special about sort of trap surface is that in every direction, either in U or V, we can't avoid the sort of caustic phenomenon.
Yes, well,
Going.
well, we can't avoid caustics unless the space-time ends first.
Right.
So in the ideal Schwarzschild case, I believe it's true that there are no caustics. Instead, they all end. But they would reach caustics, the outgoing and incoming ones, because theta is negative, would reach caustics within a known upper bound on the affine parameter if the space-time extends far enough.
Anyway, that's why it matters that it's both U and V. So
Yes, that's true.
Any way you go, you're
Yes. You see, if you go back to the case of Minkowski space, the boundary of the future of a sphere we discussed last time, it's not compact. It's got a cone, and it's got a sort of outward going cone. If you think about it, it's a manifold of codimension 1, although not smoothly embedded in Minkowski space. And it is isomorphic to S. Mapping each point to the point at the same position in space at time 0, you get a map from this thing to the initial value surface S. So the step which fails is that because theta u is positive, it's not true that the boundary of the future is compact. Everything else I've said is true, and the boundary of the future, the argument would prove that the boundary of the future is isomorphic to either S or an open set in S, and in this case it's isomorphic to S. Any other questions?
One more question, which
Yes.
is kind of a very dumb question, because it's a question about a computation.
Yes?
But it's so important, and you've stressed several times that it's one of the only cases where these
Yes.
complicated knowledge equation can do something about. The real, one of the magical things, maybe the most important magical thing, seems to be the fact that RTT and RUU are just positive. Why do they end up being positive? That's one of the dumb questions, because it's a counterfactual question. There's one population.
Yes. Yes.
But,
It's hard for me to give a philosophical answer, but I will say, I can't.
Ahead of time, it has to be positive. And then we just do the calculation to get from 1 over 2 minus 2.
No,
I said it's a dumb question.
Yes.
You can make fun of it.
Well, I am completely sympathetic with the question, so I'm not going to ridicule it at all. I would only say, what I've tried to say several times, is that what Penrose and Hawking and others who worked in this area in the 60s discovered was that you actually could extract some useful information from the incredibly complicated nonlinear Einstein equations. And this story I've been explaining is one of the few aspects of Einstein's equations where you can learn something useful without completely solving the nonlinear equations. But it's very hard to give a philosophical answer about why it was true. Maybe we'll understand it one day. Maybe people studying black hole thermodynamics will come back one day with a more conceptual explanation. Who knows? I can't answer the question. I sympathize with it. I do want to give the example of a closed universe, but are there any more questions? So for a closed universe, what's called a closed universe is a universe that's closed in the space directions. It has a compact initial value surface. Space-time is never compact by our definition. Space-time is a manifold. Time always, it might end at some fixed time, but toward the future, space-time is never compact. Sorry. Let me write the de Sitter metric at first. De Sitter space is the maximally symmetric space of positive cosmological constant. One way to write the metric tensor is what I'm writing. D omega squared is the metric of a sphere. And you see, the sphere has a radius that's exponentially big in both the past and the future. So to try to draw this as much as you can on a flat Euclidean blackboard, you might imagine something like this. Here's time. You start with, in the far future and in the far past. the cosh is extremely big, so the radius of the sphere, we could call this r squared d omega squared, where r, which is the radius of the sphere, is the cosh of t over r, exponentially big in both the past and the future. Now, as for the black hole, it's convenient to draw a Penrose diagram, which in this case is a square. T is infinity at the top, t is minus infinity at the bottom. Now, a spatial section is a sphere. But in the Penrose diagram, the sphere is collapsed to one dimension. The way that's done is that, for example, the south pole is put on the left of the diagram, and the north pole is put on the right. So the horizontal direction is latitude. The latitude on the sphere goes from minus 90 degrees at the south pole to plus 90 degrees at the north pole, or some rescaling of that. And so, as you go from left to right, each point represents a two-sphere at some latitude. Well, a d minus 2 sphere in d dimensions. At some time and some latitude. If you want to read about this example in more detail than I can explain it in the next 3 or 4 minutes, you can look at my lecture notes, but I'll try to explain the highlights briefly. So as in the black hole case, when we draw such a Penrose diagram, when we draw such a Penrose diagram, we've suppressed d minus 2 directions, which you can think of as the directions, the angles that change when you rotate around the axis from the north to south pole. And on the diagram, we've only drawn the time and also the latitude, with some choice of latitude on the sphere. So then the diagram is drawn so that light rays are at pi over 4 angles to the vertical. Now, this space-time has trapped surfaces. Any point sufficiently close to the bottom of the picture, well, any point represents a surface, but any point sufficiently close to the bottom represents a trapped surface. So it's a space-time with trapped surfaces. It's a globally hyperbolic space-time. For s, we can take t equals 0. And it's also geodesically complete. So it has trapped surfaces. Any point sufficiently close to the bottom represents a trapped surface. But despite the fact that it has trapped surfaces, it's geodesically complete, so the conclusion of Penrose's theorem doesn't apply. And there's no contradiction because Penrose's theorem requires a non-compact initial value surface. And here the initial value surface is compact. So let's see what's the boundary of the future of P. Well, we look at the outgoing null rays from P. A null ray in one direction reaches the north pole at a finite time, before time equals infinity. A null ray in the other direction takes longer, but it also reaches the south pole at a finite time. So we have a d minus 2 sphere at the point P, but when it reaches the north pole, it's collapsing to a point. When it reaches the south pole, it's also collapsing to a point. So if W is the d minus 2 sphere that corresponds to the P, then the boundary of the future of W is actually a sphere topologically. So it's compact. In the course of our proof, we proved that if the spacetime is geodesically complete, then the boundary of the future of a trapped surface is compact. Here I've more or less shown it to you in this example, although you might want to look at the lecture notes and think about it in more detail. here we have an example of a compact surface, and we check that the boundary of the future is compact. I can't resist telling you one more thing about this example, though, but I am going to discipline myself to give 1 minute for questions. Yes, if there's a question. So we've illustrated part of Penrose's theorem. The hypothesis for S to be non-compact is false in this example, and the conclusion was also false. The space-time was geodesically complete. But the example illustrates part of what was proved in the argument. In the argument, we proved that if space-time is geodesically complete, the boundary of the future of a trapped surface is compact, and this example shows that it's true. So everything is consistent. But there's something else we can do in this example, which is fun. We can consider a different initial value surface. Well, I'm just going to draw it on this picture. Unfortunately, I use the letter S for the North Pole, South Pole, and also for the surface. I'll call it curly S. So the initial value surface we used could have been the one that I drew there. That's a perfectly good initial value surface. And with that choice of initial value surface, de Sitter space is a globally hyperbolic spacetime that's geodesically complete. Now I'm going to draw another space-like surface, S prime. Except I think the picture is too busy, so I want to redraw it. So S prime is not compact. The corner is infinitely far away. Because remember, t is minus infinity at the bottom of the picture. And the cosh is blowing up near t equals minus infinity. So this corner is infinitely far away. And S prime is definitely not compact. We can't add the corner there. S prime, however, is a complete Riemannian manifold. That's because if you compute lengths along S prime, you'll find that they diverge as you approach the corner. That's because of the cosh. As you approach the corner, the time is going to minus infinity, and the lengths diverge because the cosh blows up. So S prime is a complete Riemannian manifold that's space-like, so it sounds like a good initial value surface. But is it? Well, you see, if you formulate initial data on S prime without choice of initial value surface, S prime is not a Cauchy surface for the whole space-time, because with that initial value surface, you can't predict what's happening in the shaded region. But if you throw away the shaded region from de Sitter space, so if M prime is de Sitter minus the shaded, de Sitter with the shaded part removed, then M prime, S prime, is globally hyperbolic. I just threw away whatever part of M had the property that you can't predict what's happening there from initial data only on S prime, because the corner is missing and stuff from the corner could go all throughout here. And differently put, causal curves that are trying to go to the corner never reach S prime because the corner is not in S prime. So the example M prime and S prime satisfies the hypotheses of Penrose's theorem. So let's test it and see if Penrose's theorem is true. So, well, lo and behold, there's a trap surface, the same one as before, corresponding to a point near the bottom of the picture. So the theorem says that some of the future-going orthogonal null geodesics from W is the surface corresponding to P, don't exist in M prime to infinite values of their affine parameter. And lo and behold, it's true. The ones that go here reach the North Pole, but the ones going the other way reach the end of the space-time at a finite value of their affine parameter. So the hypotheses of Penrose's theorem were true. M prime and S prime is geodesically complete with a non-compact initial value surface, and moreover, it has a trap surface. And Penrose's theorem says that this spacetime is not geodesically complete, and it indeed is not, because some of these null geodesics leave the spacetime. So the conclusion of Penrose's theorem was true, but you might be dissatisfied in the same way you may have been in an example we discussed in one of the lectures, where we discussed a special FRW spacetime as an example of Hawking's theorem. In each case, you might be frustrated because the phenomenon predicted by the theorem turns out to be, in this example, a failure of completeness rather than a singularity. The spacetime can be continued past the failure of completeness, but not in a way that's predicted from data on the Cauchy hypersurface. We really have to go because there's a class in 5 minutes, but if there's a very quick question, you can go ahead now. Okay, see you on Thursday, and don't forget, if you're interested in doing the homework, you can find the second assignment on my website.